these are some reaction examples from the first part of chapter 1 in David Klein, so that's the Enolate chapter, and specifically these are on halogenation, Aldol, and Claisen. And I've written a couple of notes on top of what was already on this handout in the PDF version. So in the first one, we have what's called a methyl ketone, although technically this will work for any ketone with alpha hydrogens, although it does work best for methyl ketones. And that just means it has a methyl group on one side of the carbonyl. And in this haloform, or more specifically iodoform reaction, the first thing that happens is that all three of the, in this case, of the alpha hydrogens get replaced by iodine. And then this is moderately reactive to a nucleophilic acyl substitution with hydroxide as the nucleophile. And so that will give us a carboxylic acid and the leaving group. And then these two just do a proton transfer. So we end up with the anion of the carboxylic acid and this substance, and this is known as iodoform, which explains the name of the reaction. And this is actually used as a test in qualitative organic analysis because this precipitate is kind of a brownish, yellowish color, which I know seems like an odd thing, but it's kind of a brownish, yellowish color. And it can be used to identify the presence of a methyl ketone in an unknown if you don't happen to have an NMR spectrometer handy to fish out that singlet at around 2.5 parts per million. You could also use it as a way of making carboxylic acids. So this second one is an aldol condensation. We have an aldehyde. And what happens in these self-condensations is that this compound acts as the enolate and as the carbonyl with which it reacts. And when I do these reactions, I like to put a little dot or something on the carbon that's going to act as the enolate, because I think it really does help when you're drawing the product. And my other trick is that usually when I do these, I write the product from the standpoint of keeping the compound that reacts as the carbonyl in position and moving the enolate up to it, if that makes sense. So we're going to start by drawing the carbonyl piece, not with the highlighter though. It's kind of running into the other one. So there's the carbonyl piece, and then I'll add to that the enolate piece. Not there though. So the enolate reacts with the carbonyl carbon, and there's my enolate carbon. So I just drew my new carbon-carbon bond. So we have one bond, and then it goes to the aldehyde, and then we have a methylene and this 5-membered ring, which I didn't attach very well. And this gives us our beta hydroxy carbonyl compound, where this is the alpha carbon to the carbonyl, the one that acted as the enolate, and then this would be the, sorry about that, this would be the alpha carbon to the carbonyl, this would be the beta carbon to the carbonyl. And again, I just use this dot as a visual aid. So aldehydes turn out to be quite good at doing self-aldol condensations. Ketones are not so good. In this next one, we have acetophenone, which some of you in Chem 24 may recognize as something we used in the Grignard reaction. And however, in this particular case, we have an aromatic ring next to the carbonyl, and we're heating it up. And so what's going to happen here is that it's not going to stop at this beta hydroxycarbonyl sort of compound, but it's going to dehydrate. And that's a combination of the heat and the aromatic ring. When I put questions on tests and quizzes, if I heat it up, that means you should do the dehydration. If I don't heat it up, don't dehydrate it. And I'm never going to try to fool you by having an aromatic compound and not heating it. It'll always be aromatic and heat, or non-aromatic and heat, or non-aromatic and no heat. So again, I've highlighted the carbon that reacts as the enolate, and I'll try to follow my own rules here and write the carbonyl compound first. And I'm going to try to save a little space here and write this initially at least as a phenyl. So there is the piece that acted as the carbonyl. And then I will bring up to that the piece that acted as the enolate. So there's my enolate carbon, and that goes to a carbonyl and another phenyl group. And because of the heat here, and because of the aromatic ring, this is going to dehydrate. I'll write it out for real now. I don't mind using abbreviations like PH and ME to work through things, but I much prefer it if when you write out things for real that you write them out fully. And you can see by doing this dehydration step that what we now have is this double bond now conjugates or provides a conjugated system from one end of the molecule to the other. Here we had conjugation here, isolated conjugation here, but it was blocked by the sp3 carbon. Now we can move the conjugation from one end of the molecule through to the other. And that's one of the driving forces for this and a reason why this particular ketone actually reacts. So this next one is an example of what's called a directed aldol. And directed aldols mean that you make the enolate first in isolation. Well, at least isolation from the carbonyl compound. And then you add the carbonyl compound slowly to the reaction mixture that contains the enolate. And the reason why you want to do this slowly is because you're trying to minimize the self-condensation of this. If you added this all at once, then you'd end up with significant amounts of the enolate and the carbonyl compound, and you'd end up with some self-condensation of this. And this is something you're going to have to do with aldol reactions where you have a mixed aldol, you have two different compounds, and the compound that you intend to react as the carbonyl compound has alpha hydrogens. And again, I've marked the location of the enolate here. Green is a good color. All right, so I'll try to follow my own rules here. So there is the carbonyl piece, and I will bring up to that the enolate piece. So remember to always put in that new carbon-carbon bond. You always get a new carbon-carbon bond between the former carbonyl and the enolate carbon. And so you want to pay attention to that. That's one reason why I do this. Another thing that you can do to help is to count carbons. You can count the total number of carbons in the two reactants and make sure that they add up to the total number of carbons that you have in your product. Anytime you do a self-condensation, you should always end up with an even number of carbons, and that's another test. And the water at the end is just to protonate the oxygen. No heat, so we're not going to dehydrate that. And there are some questions later on where we talk about when to do a directed aldol and when we don't have to do one. So we have here this rather interesting looking diketone. And this is a book example that always drives students crazy. So I always do it as an example so it will drive you less crazy. And let's see, that was purple, so maybe I'll make this purple. And it doesn't really matter where we make the enolate here, 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 or here. They're all the same. And you can make an argument that all of these positions are both inside and outside enolates. And so what's going to happen here is this is going to attack this carbonyl, and then we have to move the electrons out. So for ease of viewing, I'm going to write this as kind of the same shape, not very well though. And we reacted this with that. Kind of trying to fix the bad thing that I did there. And then we've got our carbonyl here. And so that's going to give us a 5-membered ring and a 7-membered ring, in case somebody couldn't tell from my awful ring. And I know we typically don't get 7-membered rings, but there's really no option here. And so since there is heat, I'm going to go ahead and dehydrate this, and I will attempt to beautify it as I do this. So we have a 5-membered ring, which is easy to draw. A 7-membered ring, which is usually fairly easy to draw, except here it's attached to the 5-membered ring. I probably should have done the 7-membered ring first. And let me count and make sure I have the right number of carbons. 1, 2, 3, 4, 5, 6, 7. Good. And then I'm going to put my carbonyl here. And the double bond always moves to become conjugated to the carbonyl. So that's why, for example, this has to leave. It's the leaving group, but it goes up here. It doesn't go here or here. Most of the time, that's fairly intuitive when you do these, or as was the case up here, you really don't have a choice. For some reason, with this particular problem, students or people in general tend to want to put double bonds there, but that's not going to happen. You're always going to make the double bond conjugated to the carbonyl, even if substitution patterns might tell you otherwise. So this is a reaction that we do in Chem 24, and it's actually a specific example of one that we do in Chem 24. And so what we have here is a mixed aldol. We have the compound that serves as the carbonyl compound, which has no alpha hydrogens. And then we have the ketone that reacts as the enolate. And here we don't have to resort to a directed aldol because the compound, again, that we want to have react as the carbonyl has no alpha hydrogens. And if you compare the reactivity of these two carbonyls, this carbonyl is much less reactive. So the odds of this making the enolate and then reacting with itself are not particularly good. And here I've designated the 2 enolate carbons. I sort of did an open circle here and a closed circle here. So we've got 2 equivalents. And so what's going to happen here is that we're going to make, we're going to do what's called a double aldol, where we're going to do an initial adduct and then add the other side. So let's try this one at a time. And again, I'm going to abbreviate the benzene rings as phenyl, because I don't think otherwise I'm going to fit it in very well. So we have pH, OH, enolate, carbonyl. So that's the first addition. You can argue whether this dehydrates initially or it makes the enolate and adds the other one. Who knows? It may or may not dehydrate first. I'll go ahead and dehydrate it first. I'll probably then run out of room, but that's okay. Figure that out. All right. So if that dehydrates, you would get that. And then you just repeat it again. And I think I'm stuck writing this as, well, I'll start in the middle and see how much room I have. I may be stuck writing these as pHs instead of benzenes. Now I can fit one in. Not particularly well. There we go. We've got that. And then that's really ugly. I think I need to redraw that. I think think I'm just going to stick with the pHs and not panic about fitting it in. There, that's better. All right, so then that would be our final product for this one. And notice how much conjugation we have here. You now have conjugation from one benzene ring, two sp2 hybrid carbons, carbonyl, two more sp2 hybrid carbons, and then the benzene ring. And as a result, these compounds absorb in the visible portion of the spectrum, and they're generally some kind of orange to yellow color. I'm going to write yellow, although nobody's going to be able to see it. Yellow, okay. And all of the compounds that we make 16 different ones, are orange or yellow or something like that. And that's not something that's in the book, but it's something that I like to talk about just because of the lab connection. So we will now, for the moment, leave the realm of the aldol condensation and move on to the Claisen condensation. Most of the reactions in this chapter are what we call name reactions, which means they're named after a person. So Claisen, Michael, storic enamine, all of those are people's names. Two that we've encountered that aren't people's names are the iodoform reaction that's named after one of the products, and the aldol, which is named after the fact that a beta hydroxy aldehyde, I know I'm pointing at a ketone, could also be called an aldol for aldehyde and alcohol. Another one that we'll encounter later in the chapter is actually named after the reactant. But there are a lot of reactions in this chapter that were named after people. Interestingly, one of the co-discoverers of the aldol reaction is Borodin, and he's probably better known as a musician than he is as a chemist. He was also a physician. All right, so back to the Claisen condensation. And I've always assumed that this is the same Claisen as the condenser. And again, notice that what I've done here is I've marked the enolate carbon by putting a dot on it. So the difference between ketone and aldehyde reactions versus ester reactions is that esters have a leaving group. So this group is going to leave on the one that reacts as the carbonyl. So let's go ahead and write, I'll try to follow my own rules as I said, and write the initial, write the carbonyl piece. And I'm not going to write the intermediate here. I'm just going to do that, and maybe I should do the new bond in a different color. Like, I don't know, orange, that's bilious enough. All right. I don't know why it does that, but it does. And so there's our new bond. So remember that the Claisen reaction is essentially just a nucleophilic acyl substitution where the nucleophile is an enolate. And so that's why the leaving group leaves. So we get really a nucleophilic acyl substitution. And so if we look at this carbon, it's attached to the ester, and then we have it also attached to a methylene, which is attached to two ethyl groups. And the product that we get here is known as a beta keto ester, because if you start from the alpha carbon to the piece that reacted as the enolate, there is a carbonyl on the beta position. So one way to check your work, I'm not saying you should memorize your way through this, but one way to check your work is to make sure that you do this reaction and you really do end up with a beta keto ester, or at least you end up with two carbonyl groups, one bond apart. And in this reaction, the one that I've labeled as, carbon that I've labeled as alpha, is alpha to the one that acts as an enolate. That is the alpha carbon that reacted. So it's the alpha carbon in the product, but it's also the alpha carbon enolate. And if you go back and you look at the aldol condensation, you'll see the same thing, that the alpha carbon to the one that remains a carbonyl or that keeps its functional group is from the enolate. And that's all we have to do there. So just like you can do intramolecular aldols, which I didn't do an example of here. Well, I guess I sort of did up here, but I did went through that handout. But here we have an intramolecular Claisen, which, this being chapter 21, has a separate name. There are so many condensations and many of them have names. So again, I've marked the carbon that can act as the enolate, and it really doesn't matter whether we have carbon 2 reacting with this carbonyl that I labeled 1, or we have this one reacting with that, because one merciful thing is that it's symmetrical. And so this is going to give us a 5-membered ring. So let's go ahead and draw it. I guess blue is a good enough color. Not that blue though. Well, let's see. And I'll just draw the 5-membered ring. And let's see, this is our enolate carbon. And so annoying. This would be carbon 5, this would be carbon 1. So carbon 1 becomes a ketone, and carbon 5 has the ester attached to it. And that was a methyl ester, not an ethyl ester. So we get that. And again, even though it looks a little strange compared to linear compounds, we still have a beta keto ester. And this is the one that was the alpha carbon of the enolate is now alpha to both of the carbonyl groups. By the way, the reason we have this second protonation step in the Claisen reactions is that they're driven to completion by removing this alpha hydrogen that's alpha to both carbonyls. That's an irreversible process, and it helps to drive the reaction to completion. And so here we have finally, of our last of these reaction examples, a sort of Claisen reaction and a sort of directed Claisen reaction. And I'm saying sort of because the source of the enolate here is a ketone, not an ester. So we'll start out by, again, I will attempt to follow my own rules, and I'll write the carbonyl first, the compound that acts as the carbonyl first, and then this group leaves. And then we're going to attach that to the carbonyl, or to the alpha carbon to the carbonyl, which will give us that. And now we have a beta diketone because the ester carbonyl has a leaving group on it and it leaves. And I have no idea if this has a separate name or we just call it a Claisen. Sometimes I call it a very mixed Claisen. And again, the new bond that we made, that's going to be really dark. The new bond that we made is that bond. So in this next series, we're supposed to figure out, using a Claisen or an aldol reaction, how to make each one of these 7 compounds. And again, I pre-wrote some notes on all of them. So if we look at this first one, and we kind of try to pick it apart, first of all, the molecule is a beta hydroxyaldehyde, so we know we're going to use an aldol. The OH is still there, so we're not going to use heat. And so we need to figure out what is the new carbon-carbon bond that we made. And the new carbon-carbon bond that we made is always going to be between the alpha carbon relative to the one that stayed the carbonyl and the beta carbon relative to the one that stayed the carbonyl. Now you can argue that there's another beta carbon here, but specifically when I talk about alpha versus beta, move from the carbonyl towards the OH. Or if it's a dehydration and you have a double bond between the alpha and beta, go that way. So we're going to go from the carbonyl to the other functional group. And so that alpha-beta bond is our new bond. And I've numbered both systems starting with the oxygen in 2 different colors. And this is a self-condensation. So we can just go ahead and write the structure of the aldol that we would use in some sort of a useful color. So that's that. And then we just need NaOH. And we don't need any heat. And we should have 5 carbons in that, which we do. And again, whenever you do a self aldol, you'll always end up with an even number of carbons because you're combining 2 molecules. So this next one is a beta keto ester. So we're going to make it with a Claisen. Clearly, we have 2 different pieces because we only have 1 benzene ring. So that tells us that it's a mixed. And in this book, they always use LDA for a mixed Claisen. I think because you can't rely on different reactivities. Usually when we do a non-directed mixed aldol, we have an aldehyde carbonyl and a ketone carbonyl, and we're not going to have that with an ester. And some of these, we need to, and some of them we don't. So again, look for the carbonyl that stayed a carbonyl in its original functional group. So up here we had an aldehyde. Here we have the ester. It's a little trickier because there are 2 carbonyls. Look for the alpha carbon to that and then go towards the beta. Or if you prefer, the alpha carbon is the one that's alpha to both of the carbonyls. And then the beta carbon is the one that's no longer an ester. So the one that's no longer an ester is the one whose carbonyl reacted. So this is the carbonyl piece, and this is the enolate piece. So the first thing we do here is we make the enolate, and then we add the carbonyl compound. So let's go ahead and do that. So we need to make the enolate. I'm just trying not to block it off too much. And I'm going to draw this ugly. So there's our starting enolate. So you always start with the enolate and you make LDA. And the whole point of a directed aldol is that you don't have the 2 carbonyl compounds together with the base. So you have to do this sequentially. And then our ester is going to be some sort of an ester of benzoic acid, and I'm going to go ahead and match the 2 esters. That may or may not be mission critical, but I'll go ahead and match the 2 esters, and I'll do something funny with my arrow. And then we finish that up with water. So the next one, we have another beta keto ester. So we're going to have to do a Claisen. And if we look at the 2 pieces, clearly we have 2 different molecules because this piece is longer than that piece. And so again, we can analyze this and we can look at, here's the carbon that stayed a carbonyl, and then here is the one that's alpha to it. And then we go towards the other carbonyl. So the new bond that we're going to have to make is between those 2 carbons. This is the carbonyl piece. The one that ends up as a ketone is the carbonyl piece. And the enolate piece is the one that stays an ester. So the enolate stays as an ester. And the carbonyl piece, the one that reacts as the carbonyl, goes to a ketone because it's the one that does the nucleophilic acyl substitution. So we need to get our enolate done first. And again, there's no rule that says that we have to draw this pretty, but we do have to draw it. So I'm going to draw it ugly. Well, not that ugly. So there's that piece, 1, 2, 3, 4, 5 carbons. And to this, we're going to add first LDA. And then we're going to add our 2 carbon ester. And then we'll finish up with water. In both of the, no, so in this case, no, never mind. So in this case, we have both of these compounds have alpha hydrogens. So no matter how you look at it, you would have to do a directed Claisen. If you look at this one, the blue one, this doesn't have any alpha carbons or any alpha hydrogens, and so you might think that you could get away with not using a directed, but as I said, the book always uses directed for Claisen condensation, so I'm just following that. So this next one often panics students because your eye goes on this ring and you think, oh my God, how am I going to make this thing? But remain calm. So what we have here is a beta keto ester, so we're going to use a Claisen, and we have the alpha to the one with the ester, although this ester is present as a lactone. And then we go to the other carbonyl, and so the bond is between the alpha carbon of the one acting as the enolate and the carbonyl of the other one. And this is a mixed one, so I guess we need to use LDA. Actually, there's another reason to use LDA, which hopefully I'll remember to mention. So we're going to start with the piece that we need to turn into an enolate. Trick for drawing these heterocyclic rings is to draw the ring and then stick the heteroatom in. And so the first thing we're going to do is add LDA to it, and that will make the enolate there. And then we need to add the same ester we did up there. And it really doesn't matter whether we use an ethyl or a methyl ester here. A lot of times, most of the time I'll say that everything in a Claisen should match. So the 2 esters should match if it's mixed, ideally, and then they should match the base. But that doesn't matter if you're doing a directed Claisen, because first of all, LDA doesn't match the ester anyway, and it doesn't matter that the 2 esters don't match because they're not going to be able to do a transesterification under these conditions. So this next one, we have a beta hydroxy ketone, alpha beta, and so therefore we're going to do this with an aldol. And the bond that we make, again, very boringly, is between the alpha carbon to the carbonyl towards the hydroxy one. So this is alpha, this is beta, there's the bond you're going to make. Clearly, this is a mixed aldol because these 2 pieces don't look anything alike. The carbonyl piece, that's the carbonyl piece, is going to be formaldehyde, which not only doesn't have alpha hydrogens, it doesn't even have alpha carbons. So there's no need for a directed aldol here. So again, with this one, this is the part that's reacting as the carbonyl, and this is the part that's reacting as the enolate. So we can just kind of throw everything together and assume it's going to react the way we want it to. So there's the piece that's going to act as the enolate, and we're going to add, I always feel silly if I don't put the hydrogens in formaldehyde, so I will. And then we're going to react this with aqueous sodium hydroxide and no heat. And formaldehyde is one of those classic things you can use in an aldol as the carbonyl, because in a mixed aldol as the carbonyl, because it has no alpha hydrogens. Okay, so here we go. We've got a purplish one. We've got a beta hydroxy ketone, so we have an aldol, and we need to use a directed aldol because the part that's reacting as the carbonyl has alpha hydrogens. It even has an alpha hydrogen on the product. Sometimes the alpha hydrogen in the product goes away if you do a dehydration, but if you have an alpha hydrogen in the product, you for sure have one in the reactant. So the piece on the left needs to be the enolate, and so that is our old friend cyclohexanone. So we're going to take our cyclohexanone and we're going to react it first with LDA, and then we're going to react it with this somewhat large aldehyde. And that's it. And then we need to finish it up with some water. So there you go. So again, if you have an aldol product, not necessarily a condensation, and you have a hydrogen alpha to the OH, you have to do a directed aldol because that means you have an alpha hydrogen in this piece in the reactant, which you can see here. I can explicitly put it in. And this is similar to a book one, except in the book one where I've just wrote that hydrogen, they had a methyl group. So you did not have to do a directed aldol, and I decided to change things up a little bit. So finally, are you ready? Not quite finally. We have this lovely looking thing. And again, this is related to that aldol condensation lab that we do in Chem 24. So this is a double mixed aldol reaction, like the one number 6 in the first set. And normally when you look at the result of an aldol condensation where you've made the double bond, it's really easy to figure out the bond that formed. Let me quickly go up and find one up here that actually dehydrated. So here, this would be number 3. If you look at this, the new carbon-carbon bond of your alpha-beta unsaturated carbonyl, that's the new bond. And so I think that's almost easier than when you don't have a condensation. So now we'll go back down to this one. But the problem here is that you have a plethora of double bonds. The ring ones, I think you can, everybody can see we need to excuse those. But we're going to focus on the ones that are alpha to the, or where the alpha carbon to the carbonyl is part of them. So those are the new bonds that we make. And the aldehyde that we're going to use here does have alpha hydrogens, but they're not useful ones, so we don't have to use a mixed one. I think this is a great time to abbreviate the benzene ring. So we're going to take pH, so this molecule. And notice, yes, it does have an alpha hydrogen here, but it's a vinyl alpha hydrogen, which is not useful in the context of making an enolate. And then we can take our other piece, which is cyclopentanone, and we're going to use 2 equivalents, which just means for every mole of the ketone, we have 2 moles of this aldehyde, and we're going to react this with sodium hydroxide, and I'm going to put in heat because we did dehydrate it, or we want it to dehydrate. If we were actually doing this lab, so let's say some of you come back next spring and take Chem 24 if you haven't already. When we actually do this lab, it's pretty interesting because we do 16 different combinations of compounds, and some of them react right away at room temperature, some of them react at room temperature but slowly, and then some of them you have to heat up. So there's a lot of variation in the reactivity. I'm not sure if this is the one, but one of the ones that reacts with this particular aldehyde almost works as a clock reaction because there's nothing there, and then boom, there's a lot there. This particular aldehyde, by the way, is cinnamaldehyde, and it really does smell like cinnamon. Those of you who took Chem 21 might remember brominating trans-cinnamic acid, and this really smells like cinnamon. The cinnamic acid did a little bit, but this is quite pronounced. There's our whole reaction there. I just realized I've recorded this whole thing oriented the wrong way, but that's okay. We're going to live with that. And finally, we need to look at, I guess I could be really obnoxious and rotate it, but I won't do that. Which one of these will do a successful Claisen? And all we're looking for here, the key thing to look for, makes a great multiple choice question, is that it needs to have 2 alpha hydrogens. And the reason why it needs to have 2 alpha hydrogens is that you need 1 to make the enolate and 1 to remove the alpha hydrogen, or to remove a hydrogen from the carbon that's alpha to both carbonyls. And again, that helps to drive the reaction forward. That's literally all you have to do here. So if we look at these, this first compound only has 1 alpha hydrogen, so no. This one only has 1, so no. This one has 2, so yes. And this one has 2,